Viral posts about the Great Lakes structures love claiming ancient people were too primitive to build them, implying aliens or lost advanced civilizations must have helped, but this completely ignores what archaeologists actually found. The structures use local stones already sitting on the landscape from glaciers, no quarrying, no long-distance transport, just rearranging what was there. The massive boulders weigh 4 tons, which sounds impossible until you learn that a coordinated group can move that much using wooden rollers, levers, and ice as a friction-free surface, all demonstrated through modern experiments. The real sophistication isn't brute strength, it's planning. Building drive lanes positioned exactly where caribou would travel, coordinating hunts between multiple groups, and investing labor in infrastructure that would work for generations. The myth that humans couldn't do this exists only if you assume they were stupid and disorganized, which the evidence clearly disproves. 10,000 years ago, you could walk from Michigan to Ontario. No boat, no bridge, just your feet on dry ground. The path was a limestone causeway 16 kilometers wide, cutting diagonally across what is now the center of Lake Huron. You'd walk over rugged bedrock capped with glacial till, past shallow ponds and marshes, through forests of spruce and tamarack. The air would be cold, subarctic cold. The landscape would remind you of northern Canada today, a mosaic of open plains and patchy woodlands, the kind of terrain that caribou love. Today, that causeway is 120 feet underwater. The forests are drowned, the caribou are gone. And the land bridge, the Alpena Amberley Ridge, is a silent reef that only sonar operators and divers ever see. The transformation happened because of ice. 18,000 years ago, the Laurentide ice sheet covered the entire Great Lakes region. It was a wall of ice over 2 kilometers thick in places, heavy enough to press the Earth's crust downward like a thumb on soft clay. As the climate warmed, the ice began to retreat northward, and meltwater pooled in the basins it left behind, forming the ancestors of the modern Great Lakes. But the retreat wasn't smooth. Around 10,000 years ago, the ice uncovered a critical outlet, the North Bay Passage in Ontario. This was a drainage channel significantly lower in elevation than the modern lake outlets. When the ice dam broke, water in the Huron and Michigan basins catastrophically drained through the North Bay route. Water levels plummeted. This event initiated the Lake Stanley low-stand phase. Low-stand is the technical term for when a lake's water level drops far below its modern baseline. During Lake Stanley, the water in the Huron Basin fell to approximately 40 meters above mean sea level, a staggering 100 meters below where it sits today. The Alpena Amberley Ridge, which had been submerged under proglacial lakes, was suddenly exposed. It became a dry land corridor, and it stayed that way for over 1,000 years, from roughly 10,000 to 7,500 years before present. A millennium is a long time. Long enough for forests to grow, long enough for animals to establish migration routes, long enough for humans to build infrastructure. Paleo-environmental reconstructions based on sediment cores tell us what the ridge looked like. Pollen analysis reveals spruce, tamarack, and birch, trees of the northern boreal forest. Microfossil assemblages, including testate amoeba, indicate sphagnum bogs and small Arctic ponds. The climate was cold, the summers short. This was a subarctic parkland, comparable to the modern tundra forest ecotone of northern Manitoba or the Northwest Territories. It was ideal caribou habitat, and where caribou go, hunters follow. But here's the paradox. When lake levels rise and coastlines advance, the surf zone usually destroys everything. Waves batter, ice sheets scour the bottom in winter. Coastal sites are pulverized long before they reach deep water. So how did delicate stone structures survive? The answer is what archaeologists call the Pompeii effect. The inundation of the Alpena Amberley Ridge wasn't violent. The transition from the Lake Stanley low stand to the later, higher Nipissing phase occurred as isostatic rebound, the slow rising of the Earth's crust after the weight of the ice was removed, gradually closed the North Bay outlet. Water levels rose, but the rise was relatively low energy. There was no storm surge, no catastrophic wave action. The ridge was gently drowned. Add to that the unique preservation environment of Lake Huron. The water is cold, averaging just a few degrees Celsius at depth. It's fresh, not saline, which means less chemical corrosion. It's oligotrophic, low in nutrients, which inhibits biological decay. Organic materials that would rot in months on land can survive for millennia in this environment. Acoustic surveys have confirmed the preservation quality. Researchers have identified submerged forests where tree roots are still anchored in the paleosoil, exactly where they grew 9,000 years ago. Layers of peat and gitya, organic lake sediment, are intact. Microdebitage, the tiny flakes of stone produced during tool-making, sit on the lake floor in the exact spots where they fell from a napper's hands. This is a time capsule. The hunting structures on the Alpena Amberley Ridge have remained untouched since the day the water covered them. Unlike terrestrial archaeological sites, which have been disturbed by millennia of agriculture, development and looting, these sites are pristine. And what those structures reveal is unlike anything preserved on land. Two parallel lines of stone, 30 meters long, 8 meters apart, leading to a dead end. It's not a wall designed to keep something out. It's a funnel built to trap something in. This is Drop 45, the most complex and well-documented hunting feature on the Alpena Amberley Ridge. It sits in 37 meters of water, roughly 56 kilometers southeast of Alpena, Michigan, on a strategic bottleneck of the ancient land bridge. And it was engineered with a level of precision that challenges every assumption about what primitive hunters were capable of. The architecture of Drop 45 is not random. It's a purpose-built killing zone. The site is located on a narrow, upward-sloping isthmus less than 2 kilometers wide. To the west, a raised cobble pavement, a natural feature formed by wave action during earlier lake phases. To the east, a marsh. This geography creates a natural choke point, a place where migrating animals would be forced into a narrow corridor. The Paleo-Indian hunters didn't just use this bottleneck, they enhanced it. The core of the site consists of two parallel stone lines constructed on level limestone bedrock. The stones are local materials, glacial boulders and limestone slabs, ranging in size but all manageable by human hands. The lines define a lane exactly 8 meters wide and 30 meters long. At the far end, the lane leads directly into a cul-de-sac formed by the cobble pavement. An animal entering the lane would be funneled toward a dead end with no escape route. Integrated into the stone lines are 3 circular hunting blinds. These are low walls made by piling stones, just high enough to conceal a crouching or sitting hunter. The positioning is tactical. The blinds are built directly into the drive lane, allowing hunters to strike at close range as animals pass through the corridor. The design mirrors caribou hunting structures found in the Arctic, used historically by Inuit and other circumpolar peoples. Caribou are creatures of habit. They follow linear features in the landscape, ridgelines, shorelines, even lines of rocks. Hunters exploit this by building drive lanes of brush, stone, or simply cairns, rock piles that serve as visual markers. The animals perceive these lines as barriers and naturally move between them, unwittingly entering an ambush zone. At Drop 45, sonar data reveals additional features. Flanking lines extend perpendicular to the main drive lane, widening the catchment area. These extensions gathered animals from a broader swath of the ridge and directed them into the central funnel. The total area of the kill zone, including the blinds and the cul-de-sac, covers roughly 0.28 hectares, a space 100 meters by 28 meters. But this raises a logistical problem. A structure this large, this complex, couldn't be built or operated by a single family. It would require coordination. The scale of Drop 45 suggests it was designed for communal hunts, large-scale operations targeting the massive caribou herds that migrate in the spring. Computer simulations of caribou movement on the Alpena Amberley Ridge indicate that during the spring migration, animals would move northward in aggregations numbering in the hundreds or thousands. Intercepting a herd that size required more than a lone hunter with a spear. It required a system, and systems require people. The construction of Drop 45 would have demanded the labor of dozens of individuals to move the stones, to position them correctly, to integrate the blinds into the lane. The operation of the site would have required even more coordination. Hunters stationed in the blinds, others driving the animals toward the lane, still others waiting at the cul-de-sac to finish the kill. This implies that multiple bands of hunter-gatherers aggregated on the ridge during the spring, pooling their labor to build and maintain the infrastructure. It wasn't just a hunt, it was a social event, a gathering where groups traded, formed alliances, exchanged information, and likely performed rituals. The spring aggregation was the economic and social heartbeat of life on the ridge. But Drop 45 isn't the only structure they built. Scattered across the Alpina Ambali Ridge are more than 60 stone features. From the air, or on sonar, they look random, like glacial debris tossed by retreating ice. But when you map them, a pattern emerges. Each one is V-shaped, and every V points in the same direction, upslope. These are hunting blinds, simpler structures than Drop 45, but no less sophisticated in their purpose. A V-shaped blind consists of two converging stone arms with a central area just large enough for one person to crouch. The design is elegant. The V provides concealment from multiple angles, and the stone walls offer protection from the wind, which in a subarctic environment can be the difference between a successful ambush and hypothermia. The orientation is critical. The blinds are positioned with the point of the V facing upslope or along the crest of a ridge, locations where animals would naturally travel. Caribou, especially during migration, prefer to move along high ground where they can see potential predators. The hunters knew this. They positioned their blinds to intercept animals following these predictable routes. Acoustic surveys have identified specific examples: the West V blind, the Overlook blind, each positioned on elevated terrain with clear sightlines. These weren't opportunistic hiding spots, they were carefully chosen ambush points. The difference between the V-shaped blinds and a complex like Drop 45 lies in scale and strategy. Drop 45 was designed for communal hunts, large groups of people working together to take down a massive herd. The V-shaped blinds were designed for smaller operations, individual hunters or small family groups waiting for stragglers, small bands, or animals moving during the autumn migration when herds are more dispersed. But how do we know humans actually use these structures? Couldn't they be natural formations? The smoking gun is the artifacts. Systematic underwater excavations at several blind sites have recovered lithic debitage, flakes of chert produced during the manufacture or repair of stone tools. Crucially, these flakes were found inside the blinds and immediately adjacent to the stone walls. The presence of tool-making debris confirms human occupation. The debitage also tells a behavioral story. Hunters were sitting in these blinds for extended periods, maintaining their weapons while they waited. This aligns perfectly with the ambush strategy implied by the architecture. You don't build a blind and sit in it for 10 minutes. You commit. You wait for hours, maybe days, until the animals come. In addition to stone, researchers have recovered preserved wood samples, spruce and tamarack, that have been radiocarbon dated, anchoring the timeline of the ridge's terrestrial phase to approximately 9,000 years before present. The variety and density of these structures across the ridge indicate that the Alpina Ambali Ridge wasn't marginal territory. It was a heavily utilized, intensively managed hunting landscape. The architectural diversity reveals a seasonal rhythm. In the spring, when caribou moved north in massive herds, the people gathered. They converged on sites like Drop 45, built or maintained the drive lanes, and participated in communal hunts that could yield enough meat to sustain dozens of families for weeks. In the autumn, when the herds dispersed and moved south in smaller groups, the strategy shifted. Families broke apart, spreading across the ridge to individual blinds. The hunts were smaller, more opportunistic, but still productive. This is a society that understood animal behavior at a scientific level. They knew when the caribou would come, where they would go, and how to position themselves to intercept them. They built infrastructure to match the rhythms of migration, investing labor up front for long-term returns. And this wasn't happening in isolation. 60 structures across the ridge, multiple types of architecture, seasonal aggregation and dispersal. This is evidence of a dynamic, flexible, and highly organized society. But the ridge in Lake Huron isn't the only place where underwater stone structures have been found. In 2007, a sonar operator was searching for shipwrecks in Grand Traverse Bay, an arm of Lake Michigan. The sonar pinged. The screen lit up. But the target wasn't a ship. It was a circle of stones, 40 feet in diameter, surrounded by a linear alignment of boulders extending over a mile. The media immediately dubbed it Michigan's Stonehenge, drawing a direct comparison to the iconic megalithic monument on England's Salisbury Plain. The nickname stuck, and with it came the inevitable speculation. Had someone built an ancient temple in the Great Lakes? The discovery was made by Dr. Mark Holley, a professor of underwater archaeology at Northwestern Michigan College, during a routine survey using sector scan sonar. The primary mission had been to locate and map historical shipwrecks, which are abundant in Grand Traverse Bay due to its role as a 19th-century maritime trade route. The stone formations were an unexpected find. Subsequent dives revealed the details. The stones are granite boulders, ranging in size from a basketball to a compact car. They're arranged in a circular or oval pattern, with the largest concentration forming a ring approximately 40 feet across. Extending from the circle is a linear alignment of stones stretching over a mile in length. The entire formation sits roughly 40 feet, 12 meters, below the surface. The Stonehenge comparison, while catchy, is misleading. Stonehenge in England consists of massive sarsen stones, some weighing 25 tons, carefully shaped and transported from quarries miles away. The Grand Traverse Bay stones are glacial erratics, boulders deposited by retreating ice sheets during the last glaciation. They haven't been quarried or dressed, they've been rearranged. Dr. Holley has consistently pushed back against the Stonehenge label. In interviews, he's clarified, it should be clearly understood that this is not a megalith site like Stonehenge. The site in Grand Traverse Bay is best described as a long line of stones. The comparison is one of shape, circular arrangement, linear alignment, not scale or engineering complexity. The chronology is tied to the same geological processes that exposed the Alpena Amberley Ridge. Approximately 9,000 to 10,000 years ago, water levels in the Lake Michigan basin were significantly lower than today. During the Lake Chippewa low-stand phase, isostatic rebound and the opening of glacial outlets caused lake levels to drop. The area now forming the floor of Grand Traverse Bay was dry land, a terrestrial landscape available for human occupation. The stones themselves were already present, scattered across the landscape by glaciers. The human contribution, if there is one, was rearrangement, moving the boulders into functional or ceremonial configurations. But what was the function? That's where the debate begins. Unlike the Alpena Amberley Ridge sites, which have clear hunting-related architecture and artifact confirmation, the Grand Traverse Bay Formation hasn't yielded definitive cultural material. No stone tools have been found directly associated with the structures. No charcoal for dating, no debitage. The underwater environment, covered in algae, mussels and sediment, makes visual analysis difficult, and the depth complicates systematic excavation. Some researchers propose the formation could be a hunting structure similar to those on the AAR, a drive lane or corral system. The circular pattern might represent a holding area for animals. The linear alignment could be a guide lane, but without artifacts, it's speculation. Others suggest a ceremonial or social function, a gathering place, a territorial marker, or even a navigational landmark for canoe routes across the ancient lake. The problem is that these interpretations are equally speculative. The site remains controversial within the archaeological community. Verified? No. Plausible? Yes. It requires further investigation. The current scientific status is best described as unverified but intriguing. The formation exhibits patterns that are difficult to explain through purely natural processes, particularly the circular arrangement and the extended linear alignment. Glacial action can create lines of stones, but it doesn't typically produce circles. If the site is authentic, if it's human-made, it would expand the scope of underwater Great Lakes archaeology beyond caribou, hunting into potentially ceremonial or social dimensions. It would suggest that the early inhabitants of the region weren't just pragmatic hunters, but also builders of communal spaces. But without artifacts, the Grand Traverse Bay site occupies a liminal space, too patterned to dismiss, too unverified to confirm. And then there's one stone in that formation that, if authentic, changes everything. One boulder, 4 feet tall, 5 feet long, covered in deep scratches. When you look at them from the right angle, the scratches form a shape, a back, a hump, a head with a trunk hanging down, a triangular ear, not an elephant, a mastodon, an animal that's been extinct for 10,000 years. If the carving is real, it's one of the most significant archaeological discoveries in North America. If it's not, it's a cautionary tale about seeing patterns where none exist. The boulder in question was identified by Mark Holley's team during their dives in Grand Traverse Bay. The markings are incised, carved into the surface of the granite. They're not paint or shallow scrapes. They're deep grooves, cut with enough force to remove material. The resemblance to a mastodon is striking, at least to the human eye. The outline includes features that match the anatomy of Mammut americanum, the American mastodon. A high-domed back, a pronounced shoulder hump, a downward curving trunk, and what appears to be a triangular ear. Mastodons were common in the Great Lakes region during the late Pleistocene, living alongside humans until approximately 10,000 to 11,000 years ago. If the carving is authentic, it provides a terminus antiquem, a date before which, for the site. Humans would have had to carve it while mastodons still existed, or at least while the memory of them was still vivid. That places the creation of the image at the very end of the Ice Age, making it potentially the oldest confirmed rock art in the Americas. But authentication is the problem. The scientific community is deeply skeptical, and for several valid reasons. The first is pareidolia, the psychological phenomenon where the human brain perceives familiar patterns, especially faces and animals, in random stimuli. This is the same cognitive quirk that makes people see shapes in clouds or the face on Mars. Critics argue that the mastodon is nothing more than a collection of natural glacial striations, scratches left by rocks embedded in the bottom of a moving glacier, dragging across the boulder's surface under immense pressure. Glacial striations are common on granite boulders in regions that were glaciated. They can intersect at various angles, creating patterns that, with a bit of imagination, might resemble animals or other shapes. Distinguishing between intentional carving and natural weathering requires expert analysis, typically involving microscopic examination of the groove morphology, looking for tool marks, direction of cut, and evidence of intentional design. The problem is that petroglyph experts generally don't dive, and the underwater environment makes remote verification difficult. Algae growth obscures details. Mussels attached to the rock surface. Lighting underwater is challenging, creating shadows that can enhance or obscure perceived patterns. High-resolution photography helps, but it's not a substitute for hands-on examination. Furthermore, the Grand Traverse Bay site hasn't produced any contextual artifacts, no stone tools nearby that could have been used to carve the image, no charcoal or organic material for radiocarbon dating, no debitage that would indicate a work area. The boulder exists in isolation, which makes it harder to build a case for human modification. There's also the issue of precedent. While petroglyphs are common across North America, most depict animals that were contemporary with the carvers at the time of creation. Depictions of extinct megafauna are exceptionally rare. The few claimed examples, such as alleged mammoth carvings in Utah or Texas, remain disputed, often suffering from the same authentication problems as the Grand Traverse Bay mastodon. That said, the carving hasn't been definitively disproven. Some researchers who have examined the images maintain that the grooves exhibit characteristics more consistent with intentional carving than random glacial action, specifically the way certain lines converge to form anatomically coherent features, such as the trunk and ear. But without microscopic analysis and peer-reviewed publication, this remains opinion, not consensus. The scientific verdict as it stands is plausible but unproven. The carving exhibits features that are difficult to dismiss outright, but it also lacks the definitive evidence required for authentication. It occupies the same uncertain space as the stone alignment itself, too intriguing to ignore, too unverified to accept. If future analysis confirms the carving is intentional, the implications are profound. It would establish that humans in the Great Lakes region were not only contemporaries of the megafauna, but also memorialized them in art. It would push the timeline of symbolic expression in the Americas back to the very edge of the Pleistocene. If the carving is ultimately determined to be pareidolia, it serves as a reminder of the challenges inherent in underwater archaeology and the dangers of confirmation bias. For now, the mastodon remains a mystery, a tantalizing possibility, a question mark carved in stone. But regardless of the petroglyph's authenticity, there's one aspect of the Grand Traverse Bay site that's unambiguous: the secrecy surrounding it. If you want to visit the Grand Traverse Bay site, you're out of luck. The exact GPS coordinates are locked away. No public access, no recreational diving. This isn't government censorship. It's not a cover-up. It's protection. And it's being enforced by the very people whose ancestors may have built the site. Upon discovering the stone formations, Mark Holley made a decision. He shared the precise location with the Grand Traverse Band of Ottawa and Chippewa Indians, the federally recognized tribe whose traditional territory includes Grand Traverse Bay. He did not release the coordinates to the public. The reasoning is straightforward and ethically sound. Archaeological sites are fragile. Underwater sites are especially vulnerable. Recreational divers, even well-meaning ones, can inadvertently damage structures, moving stones, disturbing sediment, dislodging artifacts. Sport divers have been known to collect souvenirs from shipwrecks and submerged features. The risk of looting is real. More importantly, if the site has cultural or spiritual significance to indigenous communities, it's not appropriate to treat it as a tourist attraction. Many tribes consider ancient sites to be sacred spaces, places where ancestors lived, worked, or performed ceremonies. Public access can be a form of desecration. This approach, sharing information with descendant communities and restricting public access, is standard practice in indigenous archaeology. It's part of a broader shift in the field toward collaborative research, where indigenous nations are partners in the investigation and stewardship of their own heritage, not passive subjects of academic study. But secrecy has unintended consequences. In the absence of public access and independent verification, online communities have filled the void with speculation. Forums and social media channels dedicated to ancient mysteries have latched onto the Grand Traverse Bay site as evidence of lost civilizations, suppressed history, or even extraterrestrial involvement. The narrative goes, if the site is real and human-made, why hide it? If there's nothing to hide, why the secrecy? The logic is circular, but it gains traction. The reality is less dramatic. The secrecy is about preservation and respect. It's about recognizing that some places belong to specific communities and that those communities have the right to control access and interpretation. This is part of a larger methodological evolution in Great Lakes archaeology. Researchers are increasingly integrating indigenous knowledge and perspectives into their work through frameworks like two-eyed seeing, which combines Western scientific methods with traditional ecological knowledge. In some regions, indigenous groups have been given microgrants to acquire their own remotely operated vehicles and conduct community-led surveys of lake bottoms, democratizing the technology and ensuring that the interpretation of submerged sites is informed by the descendants of the original builders. The secrecy surrounding the Grand Traverse Bay site isn't a mystery. It's a choice, a decision to prioritize stewardship over spectacle. The structures, whatever they are, belong to the people whose ancestors walked those lands when they were dry. That's not a cover-up. It's respect. And it reframes the entire investigation. These aren't lost sites in the sense of being disconnected from history. They're connected, directly, culturally, genealogically, to living communities. But the secrecy, the controversy, the unverified status of the mastodon carving, all of it has fueled one persistent question, repeated across viral headlines and YouTube thumbnails. How could humans have built this? Isn't it impossible? To answer that, we need to talk about physics. Stones the size of a compact car. That's how the Grand Traverse Bay boulders are described. It sounds impossible, moving something that massive without cranes, without machinery, without modern engineering. But here's the thing. A compact car weighs about 1.5 tons. The largest stones in Grand Traverse Bay weigh approximately 4 tons, and 4 tons isn't impossible. It's not even close. Let's start with material science. Granite, the type of stone found in Grand Traverse Bay, has a density of approximately 2,700 kilograms per cubic meter, or 2.7 metric tons per cubic meter. A boulder with a volume of roughly 1.5 cubic meters would weigh about 4 tons. That's the upper estimate for the largest stones in the formation. For comparison, the sarsen stones at Stonehenge weigh approximately 25 tons each. Some of the lintels weigh 7 tons. The trilithon stones at Baalbek in Lebanon weigh around 800 tons each. The average stone in the Alpina Amberley Ridge structures weighs less than 1 ton. Many are small enough for a single person to carry. The Michigan stones are orders of magnitude, smaller than true megaliths. But size is only one part of the equation. The real question is, can humans move a 4-ton stone without modern machinery? The answer, demonstrated repeatedly through experimental archaeology, is yes, and it's not particularly difficult if you understand the physics. The primary challenge in moving heavy objects isn't the weight itself, it's friction. Dragging a 4-ton stone across rough, dry ground requires enormous force because the friction between the stone and the surface resists movement, but friction can be reduced. Method 1. Rollers. Place the stone on a wooden sledge. Put cylindrical logs underneath the sledge. As you pull the sledge forward, the logs roll, drastically reducing the friction coefficient. Experiments have shown that a 1-ton stone on rollers can be pulled by as few as 10 people. A 4-ton stone might require 30 to 40 people, a labor force easily available to a community of hunter-gatherers aggregating for a seasonal hunt. Method 2. Leverage. Use wooden levers to lift one edge of the stone slightly off the ground, then pivot it. By repeating this process, you can walk a stone forward without dragging it. Method 3. And this is the most relevant for the Great Lakes context, ice. 9,000 years ago, the Alpina Amberley Ridge and the Grand Traverse Bay area were subarctic environments. Winters were long, cold, and frozen. The lakes, marshes, and ponds on the landscape would have been covered in thick ice for months each year. On ice, the coefficient of friction is close to 0. A heavy stone placed on a sledge, or even directly on the ice surface, can be pushed or pulled with a fraction of the effort required on land. A small group of people, working in winter, could move multi-ton boulders across frozen terrain with relative ease. This isn't speculation, it's physics, and it's been demonstrated. In the early 2000s, a retired construction worker from Michigan named Wally Wallington conducted a series of experiments to prove that massive stones could be moved using only simple machines and human effort. Working alone, Wallington moved concrete blocks weighing over 20 tons using nothing but gravity, wooden levers, and pebbles as bearings. He didn't have a crew. He didn't have ropes. He had patience and an understanding of mechanical advantage. If a single man can manipulate 20 tons using basic physics, a coordinated group of Paleo-Indian hunters, working in winter, using ice as a lubricant, could absolutely rearrange 4-ton glacial erratics. Moreover, the stones in question weren't quarried and transported from distant mountains. They were glacial erratics, boulders already present on the landscape, deposited by retreating ice sheets. The builders didn't need to move them hundreds of kilometers. They moved them meters or tens of meters to form lines, circles, or blinds. This is the critical distinction. The Michigan and Huron structures aren't monuments built from exotic imported stone. They're rearrangements of local materials. The labor involved is real, but it's manageable. The term megastructure fits these sites, but not because of individual stone mass. It fits because of scale and extent. The drive lanes span hundreds of meters. The hunting infrastructure covers hectares. The social coordination required to plan, build, and operate these systems is the true engineering achievement. The wonder isn't that they moved impossibly heavy stones. The wonder is that they understood their environment well enough to manipulate it, to transform a natural landscape into a functional machine for harvesting caribou. The impossible narrative exists only if you imagine them dragging rocks through summer mud with their bare hands. But they weren't doing that. They were sliding stones across winter ice. They were using levers and rollers. They were working as teams. They were engineers. And the reason they went to all this effort, the Alpena Amberley Ridge wasn't just a land bridge. It was a highway. But the traffic wasn't human. It was caribou. And the humans didn't just use the highway. They set up toll booths. Caribou, Rangifer tarandus, are one of the most important animals in the circumpolar north. Historically and prehistorically, they've sustained human populations across the Arctic and subarctic for thousands of years. They're large, providing substantial meat yields. Their hides are thick and insulating, ideal for clothing and shelter in cold climates. Their antlers can be carved into tools. Their sinew makes thread. They are, in essence, a complete survival package. But what makes caribou especially valuable to hunters is their behavior. They're migratory. They move in predictable patterns, following seasonal routes between calving grounds and winter feeding areas. They travel in herds, sometimes numbering in the thousands. And critically, they follow linear features in the landscape. Caribou instinctively move along ridgelines, shorelines, and other natural corridors. When they encounter a line of rocks or brush, they tend to perceive it as a barrier and move alongside it or between gaps. This behavior can be exploited. For millennia, Arctic peoples have built drive lanes, linear arrangements of cairns, sticks, or stones designed to guide caribou into ambush zones. The Inuit call these structures inuksut. They don't need to be solid walls. They just need to be visible enough to funnel the animals. The Alpena Amberley Ridge during the Lake Stanley Lowstand was perfectly positioned to intercept migrating caribou. The ridge ran diagonally across the basin, connecting what is now Michigan and Ontario. Herds moving north in the spring or south in the autumn would naturally funnel onto the ridge. The narrow isthmus at Drop 45, bounded by a cobble pavement and a marsh, was an ideal choke point. The archaeological evidence confirms that the people living on and around the ridge were focused on caribou. Faunal analysis from terrestrial sites in the region shows heavy reliance on caribou during the early Holocene. The stone structures themselves, drive lanes, blinds, ambush points, are functionally identical to caribou hunting features found across the modern Arctic. But why build permanent infrastructure? Why not just hunt opportunistically? The answer is efficiency. In a low-population environment, encounter hunting, wandering the landscape until you stumble upon an animal, is inefficient and risky. You might go days or weeks without a kill. Intercept hunting, positioning yourself at a place where animals must pass, is far more reliable, but it requires knowing where the animals will be. The Alpena Amberley Ridge structures represent a high initial investment of labor, gathering stones, arranging them, testing and refining the design. But once built, they could be used for generations. The same drive lane that guided a herd this year would work again next year and the year after. It was infrastructure, capital investment in future returns. This is resource management on a landscape scale. The people of the Alpina Amberley Ridge weren't just reacting to their environment. They were modifying it, shaping it to improve their odds of survival. The implications go beyond hunting tactics. The structures reveal long-term planning and an understanding that the labor invested today will pay off for children and grandchildren. That's not primitive. That's sophisticated economic thinking. But a single family, working alone, couldn't build a structure like Drop 45. They needed help, and that means they needed a society. Building a 30-meter stone lane with integrated blinds requires dozens of people. Operating it, driving the caribou, manning the ambush points, processing the kill requires even more. So where did they all come from? The traditional model of Paleo-Indian society depicts small, highly mobile family bands, maybe 10 to 20 people, moving constantly across the landscape, rarely interacting with other groups. It's a model of isolation and independence, but Drop 45 doesn't fit that model. The structures on the Alpina Amberley Ridge tell a different story. Computer simulations of caribou migration across the ridge suggest that during the spring, herds would move northward in massive aggregations, potentially numbering in the thousands of animals. Intercepting a herd that size isn't a job for a single family. It's a communal effort. The scale of the infrastructure supports this. Constructing Drop 45, gathering the stones, transporting them to the site, arranging them into functional lanes and blinds, would have required at least 30 to 50 people working over several days or weeks. That's more labor than a single band could provide. The operation of the site would have required similar numbers. You need hunters in the blinds. You need people driving the caribou toward the lane, making noise, waving, creating pressure to move the herd in the right direction. You need butchers to process the carcasses. You need people to transport the meat, preserve it, distribute it. This is a coordinated, large-scale operation, and it implies social aggregation. The model that emerges from the archaeological evidence is one of seasonal gathering. During the spring migration, multiple bands of hunter-gatherers would converge on the Alpina Amberley Ridge. They would pool their labor to build or maintain the hunting structures. They would coordinate the hunt, and then they would share the harvest. But the gathering wasn't just economic, it was social. When bands aggregate, they trade goods, they exchange information about distant territories, about where resources are abundant, about dangers. They arrange marriages, strengthening alliances between groups. They perform rituals, reinforcing cultural identity. The spring aggregation on the ridge would have been the social heartbeat of the region, the time when isolated bands reconnected with the larger community. Archaeological evidence supports this interpretation. Excavations at some of the ridge structures have recovered not just lithic debitage, but also charcoal and ash, indicating the presence of hearths. People weren't just hunting here, they were living here, at least temporarily. The presence of tool-making debris, thumbnail scrapers, quartz flakes, suggests active habitation and the maintenance of equipment. The distribution of artifact types also hints at trade networks. Some of the stone materials found on the ridge are non-local, sourced from quarries hundreds of kilometers away. This implies either long-distance movement by individuals or exchange between groups. But if the spring was a time of aggregation, what happened in the autumn? The archaeological record shows a different pattern. The smaller V-shaped blinds scattered across the ridge are better suited for intercepting small groups of animals or stragglers. These structures could be operated by one or two hunters, solo or family-sized groups. This corresponds to the autumn migration, when caribou herds are more dispersed, and families would have broken apart to cover more territory. The social rhythm, then, was one of expansion and contraction. Spring, aggregate, hunt communally, socialize. Autumn, disperse, hunt individually, prepare for winter. This is a dynamic, flexible society. not a static, isolated collection of wandering families, but a complex network of bands that shifted their social organization in rhythm with the seasons and the movements of the animals they depended on. The sophistication lies not in the stone structures themselves, but in the social systems that enabled their construction and use, the ability to coordinate labor across multiple groups, the ability to plan for future seasons, the ability to share the harvest without descending into conflict. That's the real engineering. But how do we know all this? How can archaeologists reconstruct social behavior from stone piles underwater? The answer lies in the technology that made these discoveries possible. In 2005, mapping the floor of Lake Huron required a sonar rig worth $68,000, a research vessel, and a team of specialists. In 2025, you can do it with a consumer-grade remotely operated vehicle that costs less than $5,000. The democratization of underwater technology has transformed Great Lakes archaeology from a niche specialty into a central research frontier. The discovery and documentation of the Alpena Amberley Ridge structures followed a three-phase technological evolution. Phase 1, broad mapping, 2005-2010. In the early years, researchers used side-scan sonar and differential GPS to create bathymetric maps of the lake floor. Side-scan sonar sends out acoustic pulses and records the echoes that bounce back from the bottom. The resulting images reveal topography and anomalies, places where the lake floor doesn't look uniform. This phase identified targets, features that looked artificial or at least unusual, stone piles, linear alignments, circular depressions. But sonar can't tell you definitively whether a target is cultural or natural. You need visual confirmation. The equipment required for this phase was expensive and specialized, limiting access to well-funded university programs or government agencies. Phase 2, visual ground truthing, 2010-2020. Once targets were identified, researchers deployed remotely operated vehicles and, in some cases, human divers to visually inspect the sites. ROVs equipped with cameras and lights descended to the lake floor, providing video footage and still images of the structures. This phase confirmed that the stone lines weren't glacial moraines but deliberate constructions. It also allowed for limited artifact collection, including the recovery of lithic debitage and wood samples. The technology during this phase was still costly, but becoming more accessible. High-frequency sector-scan sonar and compact ROVs reduced costs from the $68,000 range to around $15,000 and $30,000, bringing it within reach of smaller institutions. Phase 3, virtual reconstruction, 2020-present. The current phase leverages artificial intelligence, 3D photogrammetry, and virtual reality. Modern ROVs equipped with AI-driven image correction can automatically adjust for visibility issues, algae growth, and light attenuation, producing clear, high-resolution imagery even in murky water. Photogrammetry software stitches together hundreds of images to create 3D models of the structures, allowing researchers to handle the stones virtually, measure them precisely, and visualize them from any angle. Virtual reality environments reconstruct the Alpena Amberley Ridge as it appeared 9,000 years ago. Dry land, with forests, caribou, and the stone structures in their original terrestrial context. Perhaps most importantly, the cost has plummeted. Consumer-grade ROVs with HD cameras are now available for under $5,000, and some indigenous communities have been given micro-grants to purchase their own equipment and conduct community-led surveys. This democratization ensures that the interpretation of submerged sites isn't controlled solely by academic institutions, but includes the perspectives of descendant communities. One of the most innovative applications of this technology is simulation. Researchers have built virtual models of caribou behavior using cultural algorithms and influence maps. These simulations test how caribou would move across the ridge under different environmental conditions and structure configurations. By running thousands of iterations, the software can predict where additional hunting structures might be located, significantly narrowing the search area in the vast expanse of the lake floor. The technology isn't just finding structures, it's building understanding. Virtual reconstructions allow researchers to step into the past, to see the ridge as the hunters saw it, to test hypotheses about how the structures functioned. And the democratization of the tools ensures that this research is collaborative, inclusive, and grounded in multiple ways of knowing. The upcoming 2026 Society for Historical Archaeology conference in Detroit is expected to showcase the latest findings, including new sites identified through predictive modeling and additional artifact recoveries from existing structures. But even as the technology reveals more, one question remains unanswered. If these structures were so effective, if the people who built them were so sophisticated, why did it all end? What happened to the caribou? And what happened to the people who depended on them? When coastlines advance and water levels rise, the usual result is destruction. The surf zone, the turbulent, high-energy boundary between land and water, is a relentless grinding machine. Waves batter, ice scours. Coastal sites are pulverized long before the water gets deep enough to protect them. So how did the delicate stone structures on the Alpina Ambeli Ridge survive intact for 9,000 years? The answer is, they drowned gently. The inundation of the Alpina Ambeli Ridge was driven by the same geological processes that had exposed it in the first place, but in reverse. During the Lake Stanley Lowstand, water drained through the North Bay outlet in Ontario, a low-elevation passage opened by the retreating Laurentide ice sheet. This kept lake levels in the Huron Basin around 100 meters below modern levels. But isostatic rebound, the slow rising of the Earth's crust after the weight of the ice was removed, was ongoing. As the crust rebounded, the North Bay outlet gradually rose, reducing its capacity to drain water. Eventually, it closed. When the outlet closed, the lakes had nowhere to drain. Meltwater from the remaining ice sheets, combined with precipitation, caused water levels to rise. The transition from the Lake Stanley phase to the later Nipissing phase involved a rise of over 100 meters, but this rise occurred over several thousand years, roughly from 7,500 to 4,500 years before present. From a geological perspective, that's rapid. From a human perspective, it's slow. We're talking about a rise of a few centimeters per year, maybe faster in some intervals, slower in others. Fast enough that within a few generations, the landscape would look noticeably different. Slow enough that there was no catastrophic flood, no single apocalyptic event. Critically, the energy of the transgression was low. There was no massive storm surge pushing water violently inland. The water rose quietly, flooding marshes, filling depressions, submerging forests. The surf zone, when it existed, was likely mild, protected by the geometry of the basin and the limited fetch, distance over water, for waves to build. This gentle drowning allowed for extraordinary preservation. Tree roots remained anchored in the paleo soil. Peat layers stayed intact. Microdebitage, the tiny flakes of stone from tool making, remained exactly where they fell, and the stone structures, built to withstand caribou, not waves, survived. The cold, fresh, oligotrophic waters of Lake Huron further aided preservation. Cold water slows bacterial decay. Fresh water is less chemically aggressive than salt water. Oligotrophic conditions mean low nutrient levels, which inhibits the growth of organisms that might otherwise colonize and disrupt the structures. Archaeologists have described the result as a Pompeii effect, a landscape frozen in time at the moment of its abandonment, preserved under a protective blanket of water. Unlike terrestrial archaeological sites, which are vulnerable to agriculture, development, looting, and erosion, the submerged sites of the Great Lakes have been protected by their inaccessibility. Until the advent of modern underwater survey technology, they were untouched, pristine. The preservation is unique, a global rarity. Terrestrial Paleo-Indian sites are often heavily disturbed, with artifacts scattered or destroyed by millennia of environmental and human activity. The Alpina Amberley Ridge sites, by contrast, are exactly as they were left. The water didn't destroy the past, it preserved it. But when the water rose, the people were already gone. They hadn't fled the flood. They'd left long before, because by the time the ridge drowned, there was nothing left to hunt. Around 7,000 years ago, the caribou stopped coming to the Great Lakes. The structures on the Alpina Amberley Ridge were still there, functional, well-maintained, ready to intercept the spring herds. But the herds never arrived. The infrastructure had become useless, and the people had no choice but to adapt or leave. The disappearance of caribou from the Great Lakes region wasn't sudden. It was a gradual process driven by climate change and ecological succession. As the Holocene warming continued, temperatures in the Great Lakes basin rose. The subarctic parkland that had characterized the Alpina Amberley Ridge during the Lake Stanley phase, a mosaic of spruce forests, open plains, and bogs, began to shift. Warmer temperatures favored different vegetation. Spruce and tamarack gave way to pine, then to mixed hardwoods. The open, grassy plains shrank. Dense boreal and temperate forests expanded. Caribou are animals of the open tundra and subarctic parkland. They prefer landscapes where they can see long distances, detect predators, and access the lichens and low shrubs that make up the bulk of their diet. Dense forests don't provide these conditions. As the forests thickened, the habitat became unsuitable. The caribou didn't go extinct. They migrated. The herds shifted northward, following the retreating tundra and open parkland into what is now northern Canada. The Great Lakes Basin, once a critical corridor in their migration, became irrelevant. For the human populations that had built their economy around caribou hunting, this was a crisis. The drive lanes and hunting blinds, which had represented generations of labour and knowledge, were now obsolete. There were no herds to intercept. But this wasn't the end of human occupation in the region. The archaeological record shows that populations adapted. They shifted their focus to other animals: white-tailed deer, elk, smaller game. They increased their reliance on fishing, which became more productive as the lakes warmed and fish populations expanded. They diversified their diet, incorporating more plant foods, nuts, and seasonal resources. The transition from the Paleo-Indian period to the Archaic period, which occurred around 8,000 to 7,000 years ago in the Great Lakes region, reflects this economic shift. The toolkit changes. Projectile points become smaller, more suited to deer than caribou. Ground stone tools used for processing plant foods become more common. The settlement pattern shifts from seasonal aggregation sites like the Alpina Amberley Ridge to more dispersed year-round base camps. The abandonment of the ridge structures wasn't a failure. It was an adaptation. The people didn't collapse. They changed. The story of the Alpina Amberley Ridge is a story of human resilience in the face of environmental transformation. The people who built the hunting infrastructure were sophisticated enough to recognize when a strategy was no longer viable and flexible enough to adopt new ones. The caribou vanished not because they were overhunted, but because the climate changed the landscape. And when the landscape changed, the people changed with it. The structures they left behind, submerged, silent, preserved, are monuments not to a lost civilization, but to a living one. A civilization that survived because it adapted, and that civilization's descendants are still here. The viral narratives call them lost megastructures, lost civilizations, vanished peoples, mysteries with no answers. But the people who built the Alpina Amberley Ridge structures didn't vanish. Their descendants are alive today. They have names, they have nations, and they're the ones protecting the sites. The archaeological record shows a clear line of cultural continuity from the Paleo-Indian and early Archaic peoples of the Great Lakes through to the modern indigenous nations of the region. The descendants include the Anishinaabe peoples, the Ojibwe, Chippewa, Odawa, Ottawa, and Potawatomi, as well as other nations whose traditional territories encompass the Great Lakes Basin. These are not distant, unrelated groups. They are the cultural and genealogical heirs of the people who hunted caribou on the Alpena Amberley Ridge. Cultural continuity doesn't mean stasis. Societies change, technologies evolve, economies shift. But core cultural elements, language families, spiritual practices, knowledge systems, persist across millennia. The shift from caribou hunting to deer hunting, from seasonal aggregation to more sedentary lifestyles, represents adaptation, not replacement. Modern indigenous communities have been directly involved in the stewardship and interpretation of the submerged sites. The Grand Traverse Band of Ottawa and Chippewa Indians, for example, has worked with archaeologists to protect the Grand Traverse Bay site, controlling access and ensuring that the location isn't exploited for tourism or looting. The Nokiwin Tribal Council and the Red Rock Indian Band have participated in research on submerged landscapes in Lake Superior, integrating traditional ecological knowledge with Western scientific methods. This collaboration reflects a broader shift in archaeology toward what some scholars call two-eyed seeing, a methodology that values indigenous knowledge systems alongside scientific analysis. Traditional ecological knowledge, passed down through generations, includes information about landscape changes, animal behavior, and resource use that can complement and enhance archaeological interpretations. In some cases, indigenous communities have been given microgrants to purchase their own remotely operated vehicles and conduct community-led surveys of lake bottoms. This democratization of technology ensures that the descendants of the builders have agency in the investigation of their own heritage. The involvement of indigenous communities also challenges the lost civilization narrative. Framing these sites as mysterious, unsolved, or disconnected from modern populations erases the living people whose ancestors created them. It perpetuates the harmful myth that indigenous peoples were too primitive to build complex structures, implying that some external force, whether a lost advanced civilization or extraterrestrial intervention, must be responsible. The reality is the opposite. The sophistication of the Alpena Amberley Ridge structures reflects the ingenuity, knowledge, and organizational capacity of the ancestors of modern indigenous nations. Recognizing that isn't just historically accurate, it's a matter of respect. These aren't lost sites, they're ancestral sites. The civilization that built them didn't vanish, it transformed, adapted, and persisted. The underwater structures are messages from the past, but they're not messages to everyone. They're messages from ancestors to descendants, and the descendants are listening. The true wonder of the Great Lakes megastructures isn't that they're impossible. It's that they're evidence of a continuous indigenous presence in the region spanning 10,000 years. A presence that survives despite centuries of displacement, dispossession, and erasure. So when we ask, who could have built this? The answer is simple: the ancestors of the people who are still here. The viral headlines got one thing right. These are megastructures. But the wonder isn't that they're impossible. The wonder is that they were necessary, and that the people who built them succeeded. Let's revisit what we know. The Alpena Amberley Ridge structures span kilometers. They represent landscape-scale engineering, not the movement of individual massive stones, but the transformation of entire territories into functional systems. The drive lanes, the blinds, the cairns, the flanking lines, all of it was designed to exploit the predictable behavior of migrating caribou. The people who built them understood animal ethology at a scientific level. They knew when the herds would arrive, where they would travel, and how to intercept them. They possessed the engineering skill to modify the environment to their advantage, using local materials and simple tools. They possessed the social organization to coordinate labor across multiple bands, to aggregate seasonally, to share the harvest without descending into conflict. They invested in infrastructure that would serve not just their own generation, but their children's children. And they did all of this in a subarctic environment during a period of dramatic climatic and geological change, with none of the technological advantages we take for granted. That's not primitive. That's brilliant. The impossible narrative exists because we've underestimated them. We've assumed that people without metal tools, without writing, without cities, couldn't plan, couldn't engineer, couldn't think strategically. But the evidence says otherwise. The structures also reveal something deeper, the ability to adapt. When the caribou left, the people didn't collapse. They shifted. They found new resources. They changed their economy. They survived. What we're discovering now, through sonar and ROVs and virtual reconstructions, is just the beginning. Predictive modeling suggests there are more structures out there, still hidden under the silt and algae. The 2026 Society for Historical Archaeology conference will present new findings, new sites, new interpretations, new technologies. But the most important discoveries aren't technological. They're conceptual. Every submerged site we find, every artifact we recover, every structure we map, challenges the stories we've told about the past. It forces us to revise our assumptions about who could build what, when, and why. The lost civilization is indigenous North America itself, a civilization that has been systematically erased, dismissed, and underestimated for centuries. The Great Lakes structures aren't evidence of aliens or Atlantis. They're evidence of human ingenuity, of cooperation, of long-term thinking, of resilience. And that's the real story worth telling. The viral claim humans could never build this is backwards. Humans did build this. And the fact that it seems impossible to us says more about our assumptions than it does about their capabilities. So here's the final question, the one we should carry forward. What else have we dismissed as impossible simply because we couldn't imagine it? What other achievements have we overlooked? What other histories have we erased? Because we assumed that the people who came before us weren't smart enough, weren't organized enough, weren't human enough. The stones beneath Lake Huron suggest an answer. We've underestimated them at every turn, and we're still catching up. The remotely operated vehicle ascends. Its lights fade into the blackness above, leaving the stone lanes of Drop 45 in silence once again. 9,000 years of silence, interrupted only by the occasional curious fish, the slow drift of sediment, the cold currents moving across the ridge. But the silence has been broken. The structures are no longer unknown. The people who built them are no longer invisible. These aren't mysteries. They're messages. Messages from engineers who conquered ice, from hunters who read the land like a text, who understood that survival required more than strength. It required knowledge, cooperation, and the willingness to invest in a future they might not live to see. Messages from societies that gathered and dispersed with the seasons, that adapted when the world changed, that didn't need alien help or lost civilizations to achieve what seems to us impossible. They had human intelligence. They had social cooperation. They had necessity. And now, as we face our own era of climatic transformation, as coastlines shift and ecosystems change, perhaps we should pay closer attention to what they left behind. Not as a mystery to solve, but as a lesson in resilience. The impossible was never impossible. We just forgot to look underwater.